Hello everyone, my name is Hector Anapan Laval and my partner's name is Ari Wong, and we are going to talk today about network aware scheduling for data parallel jobs. Plan when you can. The authors of this paper are Virajit Jalaparty, Peter Bodik, Ishay Minaj, Sriram Rao, Konstantin Makarichev, and Matthew Caesar. They come from the University of Illinois, Urbana-Champaign, and from Microsoft. So what is the agenda for today? We're going to talk about big data clustering, its introduction, frameworks, the structure of a big data job, the issues that come with it, and the Coral framework, which is what this paper is talking about. The Coral system architecture, the design of Coral, the solution approach, and the implementation, including the overview and the policies of it, as well as the results and the conclusion. So, big data clustering. What do we mean by big data clustering, which is conformed of big data and a computer cluster? Big data is a collection of data from traditional and digital sources inside and outside your company or enterprise or business that represents a source for ongoing discovery and analysis. A computer cluster is usually composed of multiple computers connected to each other that are unified in such a way that they can be seen as a single system. Therefore, big data clustering is in a way thousands of connected computers that work together to store and compute a larger or complex data sets. So frameworks. What are the frameworks of big data? The first one is called Scope. The second one is of course called Hadoop, and the third one is Hive. The job types here are direct acyclic graph is called. Uh, this graph is a structure that consists of nodes, which is in a way the directed attribute of what we call direct acyclic graph. It means that there is only one direction from node A to node B. There's not a bidirectional arrow. In other words, we could say that from A to B is not the same as B to A, right? Acyclic, the attribute of this graph being acyclic means that you will never encounter a node you pass for the second time. It would always be just the first time and that's it. Now we're going to talk about the job type, which is called MapReduce. So what is MapReduce here? MapReduce is defined as a processing technique and a program model in which it contains two important tasks, which are map and reduce. The map part of this job is composed of a set of data which is converted into what people call tuples or key to value pairs. The reduce part of this job type is in charge of reducing the tuple that was produced by the map data input. This approach has been very attractive to companies and enterprises and businesses that look for scalability and efficiency when handling big amounts of data. And because of the way that MapReduce jobs split the data into small but independent chunks of data, it makes it in a way that they could be processed in parallel, which is of course a very practical but efficient approach. So the structure of big data jobs. So jobs consist of stages, which are composed of map, shuffle, and reduce, which are linked by data dependencies. We call map, we have discussed map earlier, which is a key to value pair. The shuffle is a sequence stage of a job, and reduce we have discussed previously. Each stage consists of several tasks. The task definition is to process input data in parallel. A task is allocated slots of the machine, the physical machine cluster, once it has all its inputs ready. The data being sent, the actual data chunk is being sent, is made up of smaller chunks. So what are the issues of big data clustering? We have network constraints. which are composed of oversubscription, for example, which limits operational costs but decreases network performance. The cross-rack bandwidth used for background data transfer reduces available bandwidth for big data jobs. We could say an example of this is Shuffle Watcher. Clustering. The issue with clustering is that reading data across racks is usually heavily congested. Shuffle and join. It involves transferring large data across networks. So that's definitely a big a way. There has to be a way to reduce a way to transfer large data across network, which could be, of course, to break it up into smaller data chunks. So what causes these issues in big data clustering? We have inefficient job scheduling. We have which is composed of data location, which is spread across racks in the cluster to avoid network contention. Another one is the data compute location. They're not optimized jointly. What does this mean? This means that we have an improper placement of data and tasks, which cause network flows to use congested network lines. So what are some motivations, some improvement ideas for big data clustering? One of them is the job input data. What can we do with job input data? One of the approaches that have been discussed here is to place job input data in a fixed designated location before the job actually executes. So we have we can have upload data to a desired and a specific location. For example, the way that ClickLogs do it. The location is usually where most of the input data is located on. So job input data is stored in a separate storage cluster, such as we can say, for example, Amazon S3 or Azure Storage. So another motivation in order to improve big data clustering is by using existing job schedulers which schedule network flows. We have examples of Varis or a Barat. So these are flow level techniques to schedule network transfers, but assume that source and destinations are fixed. So what does this mean? That no dynamic scheduling occurs. We have Sinbad, which is composed of scheduling flows around network contention. So what are some predictable characteristics? We have 40% of production jobs that are recurring, meaning that these jobs can be placed in the most efficient network localities. So recurring jobs in themselves are usually have predefined submission times and predictable resource requirements. Therefore, for every instance of that job, it usually has a fixed structure and similar characteristics, which are composed of the amount of data transfer and shuffle, or CPU and memory demands. We have the same script to process data. So recurring jobs execute the same script to process data whenever new data becomes available. What does this mean? The historical information can actually accurately predict a trend, which enables us to plan ahead. What does this mean? Due to job predictability and improved network locality algorithms or concepts, it is possible to run a bulk of jobs within a subset of racks without losing parallelism. So big data clustering, still working on some more improvement ideas. So what are some other motivations and thoughts of improvement here? It is possible to run a bulk of jobs within a few racks without losing parallelism, as we have been able to prove, as we have discussed earlier. So we have this figure on the right, which shows that ultimately we can be more efficient when it comes to using repetitive and jobs that have the same trend, the same trend exactly. A second motivation would be to achieve better locality by jointly optimizing the placement of data and compute in big data clusters. So this is what the Coral framework is trying to do. So what is the proposed solution? It's called Coral, as we have discussed earlier. So, based the proposed solution to issues described is what the framework comes in, and this Coral framework would come into play. So, what are the main aspects of the framework? The very first aspect of this framework and its main goal is to exploit the predictability of future workloads to jointly optimize the placement of data and compute in big data clusters. So, due to this main aspect, job performance and allocation is much better managed, and the job management is much more efficient as well. So, the system architecture of Coral. What are the components of Coral? The first one is called the offline planner, and the second one is called the cluster scheduler. So, what are these things here? We will discuss in a few. What is the diagram scenario? The step one, as we see on the figure on the right, the first step is it involves offline, which it involves the offline planner to receive future workload estimates. So, in a way, the offline planner receives estimates of characteristics of jobs such as arrival time, input data size, etc. This estimated data will be later submitted to the cluster in the future. So, what does the offline planner do? It uses these characteristics to estimate job latencies or jitters and solve an offline planning problem in order to minimize some metrics such as the make span, which we can define as the average job completion time. So, what are we talking about is step two, based on the figure on the right. What happens is that we upload the input data of a job into the cluster scheduler. Then, what the Coral framework does is to place one replica of each data chunk in a random rack, let's say R, and the other replicas are allocated in another rack that is not the rack where the first replica was placed on. So, step three, we have it mainly consists of submitting the job in specific to the job scheduler. So, in a way, we make sure to constrain this task to be scheduled only within the subset of racks where the input data was placed on, which also include the replicas. So, what do these steps do here? These steps would ensure that the framework scheduler is able to achieve data locality not only in the initial stage of a job, which the initial stage of a job is usually defined composed of map and extract attributes, but also on the subsequent stages of a job, which could be reduce and join. There is also a priority factor for each job, which is needed in order to ensure that the order of which jobs are scheduled by the cluster scheduler matches what the offline planner is telling it to do. If for any reason, any racks in which data chunks have been allocated, if these data chunks for some reason fail, then the cluster scheduler will ignore the guidelines for that job and use randomly selected machines in the cluster to hold data in order to keep the process going. When it comes to ad hoc jobs, an existing technique of the distributed file system will be used instead of the Coral technique. So a traditional technique would take place in here instead of the Coral framework approach. So one of the components of Coral is called the offline planner. So what are the functions and capabilities as well as the main goal of this component? We receive estimates of characteristics of jobs, as discussed briefly in the slide before, which are data like arrival time, data size. We are talking about here like CPU and memory usage, and other job requirements, depending on what the requirements of the specific job is. We use estimates for latencies for the offline planner. We solve the offline planning problem with the goal of minimizing a specified metric. We can talk about make span or average job completion time. It creates schedule consisting of a tuple, which is a key to value pair, which is mathematically defined as in the mathematical definition is called RJ and PJ. What is RJ and PJ? RJ is defined as a set of racks on which job J has to run, and PJ is a priority of the job. So, what are the main goals of the offline planner? The main goal of the offline planner is really to optimize job execution while addressing important challenges. What are the challenges here? The main challenges are to determine which racks to assign a job in order to maximize network locality while keeping parallelism. And the second one is to ensure that jobs and their input data are spread across the cluster without overloading any part of it. So the second component is a cluster scheduler. What are the functions and capabilities of a cluster scheduler? The first one is to use schedule generated from the offline planner. What does this mean? We use a guideline to place data and tasks when running jobs on the cluster. The second one is to constrain its tasks to be scheduled within the racks in RJ. The third one is to ensure data locality during subsequent stages and not just initial stage. For example, the subsequent stages could be reduce and join, and initial stage jobs are map and extract. So what are the objectives of this Coral design? In regards to the offline planner, we are talking about generating predictability guidelines based on job characteristics. We feed the guideline to the cluster scheduler. So what does the cluster scheduler do? What is the objective of this cluster scheduler as part of the Coral framework? We are talking about using guidelines for data and computing task placement. Overall, we are talking about optimizing network locality for each job, as well as improving overall performance. Overall performance really is composed about reducing network contention, as well as the cross-rack dependency that big data centers are trying to improve. So in order to design this Coral framework, they have figured out two scenarios in order to work with. The batch scenario it mainly consists of multiple job submissions of a batch, let's say a batch script, to the cluster at the same time. What is the goal of this batch scenario? Is to minimize the make span. For the online scenario, we have the job. It consists of having job arrivals over a long period of time with a known arrival time. What is the goal? What is the goal of this scenario? Is to minimize the average job completion time. So, what are the challenges that we have for this Coral design? The first one talks about the level of guideline granularity. So we need to make sure to define what granularity we're going to work with here. This mainly is discussing providing a target machine for each task of a job. That's one option. Another challenge is to have manageable with existing big data systems. The third one is to identify and prove out methods to estimate job latency of a particular configuration. So what are the solution approaches to these challenges discussed? In regards to the granularity challenge, there are many different granularities for each problems. So we have the level at the task level, which talks about having which tasks of a job should run on which machine on the cluster. Right. So we have job input sizes can be predicted with small error, but no task input sizes. The task input size depends on data partitioning, which is definitely, is practically unpredictable, as well as the number of tasks. So what are we talking about as far as the stage level goes? What if we take this approach? The stage level it mainly specify which rack or racks each station a job should use. In a way, we're talking about job stage to racks in a cluster. So based on some tests being done, as shown in this paper, very few DAG jobs provide locality benefits. So as we talk about, DAG is direct acyclic reps. So when we talking about the racks and jobs level, we can see that there's definitely some scalability improvements and robustness of the offline plan. planner. It allows the assumption that tasks in a rack can communicate at NIC speeds, at efficient NIC speeds, which simplifies the modeling of job latency. This is the recommended approach that we're going to use in order to overcome these challenges, to try to overcome these challenges. So, and the second challenge was to formalize the offline planning problem using malleable job scheduling. So what is really a malleable job, right? A malleable job is a job whose latency depends on the number of resources allocated to it. In other words, these jobs are very flexible and dynamically structured to change depending on the resources that make part of it. What is the planner decision here? Is to have the number of racks to process the job stacks, which will affect the job's latency. What is the third challenge here that we're talking about? It's the job latency with simple response functions. So what do we do here? In order to characterize job latency, the first approach, which is the first bullet that talks about using historical job characteristics to generate analytical models in order to compute job latency. In order to characterize job latency, this approach is used to model job latency as the number of racks allocated as well as fixed job characteristics, in which some options for them could be the amount of data transfer across racks, CPU resources required, as well as maximum parallelism for the job. Using these historical job characteristics will lead us to derive simple analytical models to compute job latency. So we have actual job latencies that depend on additional runtime factors such as failures, outliers, simultaneously job executions, as well as using approximate latency models, which most likely suffices for significant latency improvements. So the actual job latencies really depend on additional runtime factors, but since a latency approximation is only used for offline planning, they are willing to trade off actual accurate latency values for more simple and practical planning algorithms due to the fact that they're also efficient to test with. So what is the trade-off that we're talking about here in order to have accurate job latencies and approximate job latencies? What is the trade-off here? The offline planning from accuracy to simpler and practical algorithms. Also, the responses provide abstraction over various factors that affects latency. So the simple response functions have some benefits, such as providing abstraction of various factors that also affect job latencies, as we've talked about, such as maps and reducers, which enables us to plan for jobs to minimize the required metric without modifying core algorithms of the framework, the core framework that we're trying to test with. So we're going to talk about the problem description in Coral. So we have a set of jobs J that have to be scheduled on a cluster of racks, which we'll be calling R. The latency response function is defined as LJ equals 1, R, which provides the estimate job completion time. What are the assumptions that we're working with here? Actually, let me go back and talk about a little bit more about the second bullet. So each job is characterized by a latency response function, which gives the expected job completion time as a function of number of racks assigned to the job, if that explains it better. So the assumptions here are the assigned subset of racks will be used until job completion. It'll be a more simplified problem formulation. And even with deviation from these assumptions, Coral still outperforms existing schedulers. So our main goal here for the offline planning is to minimize the average completion, which is the arrival of job unto completion. We're trying to minimize this completion time of the job. So what are the heuristics that we're working with here? How do we solve this planning problem? How do we overcome it, right? So we determine the amount of resources, which are the number of racks in this case, to be allocated to a job first of all. Also, where to allocate those resources in the cluster. Also, to decouple the planning problem into two phases, which would be discussed later. These are provisioning phase and the prioritization phase. And One of the values would be TJ, which is calculated in the prioritization space, which determines the job ordering priority. So we're now going to talk about the provisioning phase. So the main purpose of this provisioning phase is for each job J, we determine the RJ, which are the number of racks allocated to that specific job. So the initial test as part of this implementation test is to have one rack, start off with one rack, which is mathematically equal to RJ equals 1 per job. So as we go through the iterations, we need to identify job J with the following features. We have job J uh, allocated to have less than R racks, and job J which has the longest execution time. And as we go through each iteration, we increase the job allocation by one rack. After each iteration, we find the job which is allocated less than R racks and has the longest execution time according to the current rack allocations to the job. The iteration finishes when R when when has R racks allocated already for all jobs with RJ allocation. This algorithm works. Why does it work? Because it spreads the longest job across more racks, shortening the job that is taking out the most. So we're trying to make this job as small as possible, and working with efficiency and productivity of this approach. So we're going to talk about the prioritization phase here. So if we talk about in the batch scenario, we're talking about how to make the widest job first a little bit more efficient. This is to avoid holes in schedule. Also, we're going to talk about the longest job, in which the main factor is the processing times. Also, the iteration will go until all jobs have racks. So if we take a look at the online scenario, in which jobs are sorted in ascending order of their arrival time, we're gonna take the first come first serve approach, and take a look at the longest job, in which the main factors is of course the processing times as well. So how do we estimate the quality of this heuristic, right? The suboptimal ultimately is suboptimal to break down the problem into two phases. So when we're talking about the batch scenario here, it ultimately finds a schedule with the resulting make span within 3% of a solution of an LP relaxation to the planning problem. When we talk about the online scenario, we find a schedule with the resulting make span within 15%. So what are these results show? What does these results show? It shows that the two-phase approach is a near optimal solution, but it's not quite there yet. So what are we doing with this implementation with the Coral framework? We have the two main components, which is Apache Yarn frameworks, which is Hadoop to that 4. Apache Yarn, it is another name for MapReduce 2.0. Therefore, it is a cluster management technology to manage resources in order to provide a large-scale distributed operating system for big data applications, such as the one being proved out here, which is the Coral framework. So we're talking about also the Hadoop Distributed File System, HDFS. So what is HDFS? It is mainly defined as the primary storage system used by Hadoop applications that provides high performance access to data across Hadoop clusters. So we gotta use policies to ensure the offline planners output are respected. So we're gonna talk about first the data placement policy. We're gonna make some changes to the traditional policies that Yarn and HDFS use in order to prove out that the Coral framework results will be much better and much more efficient. So as far as the data placement policy, we are going to modify HDFS create method of this API framework in order to include a set of tuples defined by a rack ID value and the number of replicas for the data chunk that we're talking about specific. What is this done for? This is done to ensure that at least one replica of a data chunk is placed on a machine which belongs to the rack specified. So we're gonna make some changes to the task placement policy. Traditionally, Yarn uses an application manager to request slots from a resource manager, the RM, and Coral modifies the default behavior, which is to let the application manager allocate tasks for maps only, and it lets the app manager allocate all tasks, including the reduced jobs as well. So in the event that the allocation of a task is not available due to any issues such as machine failures or any type of unreachability, what does the resource manager do? It ignores the locality guidelines and assigns slots on available nodes in the cluster. So what are the evaluations results in result number 1? We have evaluated Coral framework to the traditional Yarn's capacity scheduler. So when we use the MapReduce workload, we can see big improvements, as we can see here. We have 10 to 33% reduction in make span, which is huge. Also, 26 to 36% reduction in average job completion time. As we can see on the figure on the right, it plots cumulative fraction over jobs of this metric for Coral and Yarn CS. We can see in the figure here that the results are very interesting, and it shows that regardless of us using an approximate approach, we can see that Coral is much better to work with over the traditional Yarn capacity scheduler. So if we use Hive queries, we can see that the average we can see an average 21% improvement in completion time. So for result number 2 of this evaluation is to use Coral framework for recurring and ad hoc workloads. So when it comes to recurring jobs, we have an average 33% improvement in completion time. So you can see in the figure below that Coral is the black line and Yarn CS, the capacity scheduler of Yarn, is the orange line, and we can see a pretty big improvement here. When it comes to ad hoc jobs, we can see an average 20% improvement in completion time. So regardless what type of jobs we're talking about here, we're going to see a much bigger improvement as compared to the traditional approach. So we made a sensitivity analysis as part of the conclusions that we made. So what are the benefits of Coral? They really depend on the following. We have the network load. So Coral gains increase significantly as network usage increases, as shown on top of figure 12 on the right. The accuracy with which jobs characteristics can be predicted. The benefits of Coral in a make span reduction are between 25 to 35% lower compared to Yarn CS. So, some conclusions on existing solutions. Data placement and computing location are not coupled. They don't jointly optimize. So, if they don't jointly optimize, what's most likely going to happen is we're going to see an increased amount of contention to an overly subscribed network. So, what are our thoughts on this? There is a legitimate concern with details to justify widths in both theoretical and practical ways, as well as focus on concepts and on-the-spot processing, but not optimization. Oh, conclusion on Coral. We're talking about to consider future workload. Obviously, as discussed before, we need to find a way to jointly optimize the location of both data and tasks. What does this mean? We need to reduce network contention and to run fewer cross-rack jobs. We need to also provide offline planning, as discussed earlier. This is definitely an efficient way, an efficient approach is to use the offline planner. What are our thoughts on this? We have advantages over existing solutions, as proved out earlier. is to definitely jointly optimize over data and compute locations, and the offline planner to allow planning ahead, which is a very important concept, predictability, right? Planning really is a common concept used in many areas, like let's say SDLC and project management. Thank you very much. And my presentation has been about network-aware scheduling for data parallel jobs. And thank you. Have a wonderful day.